Okay, so we've got 9 items, so it's not going to subdivide nicely. Okay, normally they'll do something like 8, but if I was setting the paper, I would put an odd number on, just to check that someone understands how the subdivision works. So, just like with all the other, whenever you're showing arrays or lists, don't do boxes, just do like we would if we were doing it on code. Just use square brackets to mark the extents. If you want to put commas, but hey, who wants to write even more ink on the paper? So I'm just leaving a gap. Depends how bad you are at writing numbers. If all your numbers look like individual digits, then yeah, put commas in. But I'm trying to actually group mine a little bit. Right, so the first phase of that merge sort is to identify individual lists. So we're going to split this list until we get down to singles. Because we know, because of the standard premise, if you've got one item in a list, that is automatically sorted. And that's the starting point for the merging process. So we have to do that first. Now, you could, because we can do it, because we're human, we could say like, well, there's 19 lists, let me just write down 19 lists. Okay, and I think in general, when they're marking the answers, if you look at the mark schemes, they just want to see that you've identified individual lists. But let's go through the process anyway. So we take a list of 9 and we split it into 2. Obviously it doesn't fit nicely, so we can do a 5 and a 4 or a 4 and a 5. Okay? But you only split into 2 lists each time. So don't like say, oh, I'm going to be clever and split it into 3. No, you just divide it by 2. So I'm going to make space, and ideally when we do this, we shouldn't ever need to get any wider than that. Okay, so my extent of my list, I'm going to split it into 2, so I'm going to do 5 and 4. So I'm going to go split it into 2 lists. So that's list 1, and the other sub list is that one. So this split process in the merge sort algorithm continues until we get down to an individual list. So we can now like just take this one and split that one down. So let's take this list and split it into 2, and again it's not a nice number, so I'm going to do 3 and 2. So I've got a 12, a 4, 19, I've got a 7 and a 31. I'm not trying to sort, I'm doing nothing with the numbers. All I'm doing is I'm working out the positions of all the individual sublists. This one I'm going to split. This one's an even number, so this splits nicely into 2 2s. Okay, and I've got to keep doing this split process. So take this one with 3 in it. That's now going to split into a 2 and a 1. So the 19 list, that's done. This one splits into 2 singles, so they're done. And these other 2 will split into singles. So we're nearly there. So this is the recursive part at the start, where it just says, as long as I've got more than one item, go into the merge sort and split it again. Okay, so everything's got to be done. This one is the last one to split. So we then end up with the quite obvious, but too obvious you can't spot it, premise that every single one of these lists is now sorted. And then we can get onto the detail of what the merge sort does. Okay, so we end up with a load of single list items, which we can hand on heart say they are all sorted. So the merge process isn't essentially sorting, it's just saying, right, let's have a look at 2 lists at a time, and let's just read from those lists of the smallest one each time. Okay, so like I say, you can jump straight to this. They seem to accept that in the mark scheme, but I would always put some commentary at the side and say recursively split lists to get to this point. Single item lists are sorted. Okay, just something like that. Right, so I'll just scroll this up so I can see what I'm doing. So all I'm going to do is I'm going to take a pair of lists. and it's usually a pair of lists that are adjacent. I don't know whether there's any benefit of doing anything else, but really, because it's going to be merging the changes back to the original list, we need to make sure that we are only occupying the memory locations that we're going to overwrite with the new changes. Because remember, the downside to merge sort, it's only Achilles heel, is it needs to make new space. So when we do this merge process, we're not going to affect the original data set. We are going to create a new bit of space. Okay, so we show that by actually creating space for 2 data items, because that's what we're going to merge to start with. Okay, so we put markers at the head of each list. Well, this is a bit weird for the first one because there's only one item in there. All right, and we just look at the 2, and you can do this with files. This is where this came out of merge sort. These could be pointers in a massive file of numbers, okay, that are sorted, and you can merge 2 massive files. If you haven't got enough space in memory to hold all your data, if they're in files, you can merge them. All right, so we're just going to say, right, 12 and 4. We'll go. Let's go descending on this one. So we're going to go descending order. So which one's the biggest? 12. So we're going to write the 12 first. Then we're going to move that pointer on, and we're going to say, oh, hang on a minute, the list is ended. So what that means is we don't need to do any more comparisons. What we're going to do is dump the contents of the list. Now, yes, I know this is odd because there's only one item in there. So what are we gaining here? But that's the process. So we dump the 4. It's exhausted. We've done it. So we've now created a list of 2 items that are in descending order. Okay, and we move on to the next pair. And it's all about those pointers. So I make the space first, put my markers at the head of each sublist, and I say which is the biggest. Well, in this case it's 19. So I write 19 down, move that pointer. So I'm annotating this, I'm putting a little arrow there to show that I've moved the pointer. I can see I've got to the end of the list, so I dump the contents of the other one. And one of the things that makes this quicker than quicksort is the fact that we're minimizing comparisons. Okay? So as soon as we've exhausted the list, we can go bang. We just dump the other one. It's just a copy process, which can actually be done really quick if you're using cache or you've got hardware that can do DMA transfers and things like that. Right, so next pair, make my space. I don't know why they're getting taller, these lists, but they are. I'm just going to try not to get any taller.
Where did you put the whiteboard?
I did link it on the... oh, did it not post? Hang on, let me check.
No, people are already watching it.
Oh, it is on there, yeah. It's on the course progress one.
Okay.
Not for you, obviously.
Teams is having
Teams doesn't like you.
today.
No, it's happy. It just doesn't like you, David. Right. So we go to the next pair. 31 and 10. So 31's the biggest. So we write that one down. Move on in that list. We got to the end, so we'll dump the contents of the other one. It literally is a dump. Move on to the next pair. We got 2 pointers. 15 and 5. Want the biggest, so 15 goes in first. Move it along. Oh, we got to the end of that list. Dump the other one. 3 is all on its lonesome. So we don't do anything with 3. There isn't a pair for it. We will pick up that single right at the end. Okay. Right, so that was the first phase. So we've ended up with a load of individual lists that were in order, and now we've got 5 lists that are still in order. So we've got 12 and 4, we can just double check, 19, 7, 31, 10, 15, 5, and then lone layout 3. Okay, so we're just going to do the merge again. Next phase of the merge is just going to take pairs again. So we've got 2 pairs, we need space for 4. I'm going to go back, I can't go back to 2, I'm going back to 2.5. There's my height. Those guys. Right, so I made the space for 4 items because that's what's contained in my 2 sublists. They're adjacent sublists. So 12 and 4 and 19. 19 is the smaller. move the pointer on, so we're at 7 now. So we compare 7 and 12. 12 is the larger, sorry. We move that pointer on. We now compare 4 and 7. 7 is the larger. Move that one on. Oh, we've got to the end. So let's just dump the contents of the remaining list. So that's the 4. Okay, so double check. 19, 12, 7, 4. So we've maintained the descending order. Let's do the next pair. And while we're there, we'll just write the lonely old 3 down. Because we're not going to do anything with 3 yet. Right, so put a couple of pointers to the heads of each one of those sublists. So we've got 31 and 15. So 31's bigger. So we write that one down, move on in that list. So we're now comparing 10 and 15. So 15 is the bigger one. Move on in that list. Comparing 10 and 5. So 10 is the bigger. Move on in that list. Oh, we've got to the end. Dump the contents of the second list. Okay. So at this point, we've done 2 phases of merge. We've got 3 lists that are hopefully in descending order. So 19, 12, 7, 4, yeah. 31, 15, 10, 5, and then 1 now 3. Right, so we've got another phase to go. So we're just going to create the space. We need space for 8 items this time, because there are 8 in total in these 2 adjacent sublists. Let's put our pointers at the start of each. We're going descending. That's what we must not screw up in the question. Right, so 31 is the biggest, 31 and 19. Can you see how, as well, compared to quicksort, there's not so much jumping around? We are actually, because these are next to each other in memory, and we're just incrementing pointers, we can take advantage of cache that's on the CPU. So we get a massive free speed boost. Obviously, once these start getting big, it might not fit in the cache, and then you're going to get loads of cache problems, cache misses. But we won't worry too much about that. Right, so 31 got written down. So we move on in that one. So we're now comparing 19 and 15. So 19 is clearly bigger. So move that pointer on. Now we're comparing 12 and 15. So 15 is bigger. Move that pointer on. Comparing 12 and 10. 12 is bigger. Move that pointer on. Comparing 7 and 10. So 10 is bigger. Move that pointer on. 7 and 5. 7 is bigger. Move that pointer on. 4 and 5. 5 is bigger. Move that pointer on. We've exhausted that list. Dump the contents of the other one, which is just the 4. Long now 3. E comes down. Right, we've got 1 phase to go because we've still got 2 lists. And we're going to merge these 2 together. Okay. Right. So we need space for 9 items. So let's make space for 9 items. And that's where we're having to request space. You can do this cleverly by having just 2 arrays. Don't keep reallocating arrays because obviously that would kill this, especially as you start getting deep. But yeah, you would set up at the start, you'd say, right, well, I've got an array of 9 items. Let me make another temporary array to do all this like shuffling around. And then we can copy back. Right, so 2 pointers. 31 and 3. 31 is bigger. Move on. 19 and 3. 19 is bigger. Move on. 15 is bigger. Move on. 12 is bigger than 3. We haven't moved the other pointer yet. Move on. 10 is bigger than 3. Move on. 7 is bigger than 3. Move on. 5 is bigger than 3. Move on. 4 is bigger than 3. Exhausted that. Dump the contents of the single item. And there we go. I'm going to do a straight line just because I can celebrate using the shift key. It tells everyone I'm doing it though. No, I'm not doing anything clever. You're all going, yeah, you're just on shift. There you go. Right, so that is the process. It's agnostic, merge sort. It always does the split and it will always do the merge. There isn't much difference in work. I mean, in this case, When we got to the dump stage, it was always just a single item. So you do get variability. If we were going ascending, we'd have written the 3 first, and then all the rest would have got dumped. And then that would have been quick, because that would have been like you could have done a DMA transfer on that. Okay, anyone got any questions about that? So obviously it's slightly easier if you've got a binary count, because you're just going to like subdivide. You won't get any like little orphaned list at the end. But please don't try and merge through it once. When we're doing file merging, you might actually hook up to 10 files at once, because you only need enough memory to hold one item from each file. So you could do 100 files at once. If you had 100 sets of data in files that you knew were sorted and you wanted to merge them all together, yeah, you could do 100. You make your algorithm a bit weird. But there's nothing to stop you doing that and then spitting out to another file. So don't hold anything in memory, just write out to files. You used to do that a lot with tape, because tapes can be read and written really quick.